Methods of detecting exoplanets to be discussed here are the astrometric method, or imaging, the Doppler method, the transit method, and using gravitational microlensing. The astrometric method involves repeated imaging so that planetary motion can be observed. Imaging is a challenge due to the parent star being so much brighter than any orbiting planets. The greater the angular separation between the planet and star, the easier it is to image. Systems that are closer to Earth and systems where the planet orbits at large distances from its parent star are more likely to have greater angular separation. At optical, visible wavelengths, stars emit an enormous amount of light, whereas planets don't emit visible light and generally only reflect a relatively small amount of the starlight. However, planets do emit infrared light. Although stars also emit infrared radiation, planets tend to stand out more and are somewhat easier to image at these wavelengths. Modern instruments have imaged exoplanets at both infrared and optical wavelengths. When a planet orbits a star, both the star and planet orbit about a center of mass point between them. Center of mass can be explained by imagining two objects that are connected with a rigid rod. These could be two stars or a planet and a star. The center of mass point is where you would have to put your finger to balance them. You would have to put your finger nearer the more massive object. If one had two stars of equal mass, then the center of mass point would be right at the center. Shown as how mass and velocities are related to the distances to the center of mass points. Notice that the more massive an object is, the closer it is to the center of mass point and the more slowly it orbits. For example, a star with 1/3 the mass of another orbits 3 times farther from the center of mass point and orbits at 3 times the speed. Because stars are generally much more massive than planets, the center of mass point for a star-planet system is very close to the center of the star. As a result, the star may only wobble around that point while the planet orbits at a large distance at a much higher speed. The motion of the star can be detected by measuring the Doppler shift of the starlight as it wobbles. Over time, the light gets alternately red-shifted and blue-shifted. Many spectra are taken over many nights in order to amass enough data to reveal how the radial part of the star's motion varies over time. A plot of the radial velocity as a function of time is called a velocity curve. Information about the planet and its orbit can be gleaned from this curve. Shown is a simulated comparison of a velocity curve for a star with an orbiting planet on top and the same star with a more massive planet on the bottom. The planet is orbiting at the same orbital distance in both cases. A star with more massive planet orbiting it will have a velocity curve with a greater maximum velocity. If the star mass is known, it is often possible to calculate the mass of the orbiting planet. Again, a star with an orbiting planet is shown on top and the same star with a planet orbiting at a smaller orbital distance is shown on the bottom. A star with a smaller orbital distance have a velocity curve with a smaller amount of time between its maximum velocities. The time between maximum velocities is the period of the wobble of the star. This period is also the orbital period of the planet. The planet's orbital period can be used to calculate its orbital distance. As expected from Kepler's third law, the closer a planet to its parent star, the shorter its orbital period. Summarizing the last two slides, the shapes of the velocity curves can be used to determine the mass, orbital period and orbital distance of the planet. Orbital eccentricity, and the orientation of the orbits with respect to Earth, also affect the shapes of the velocity curves. Thus, these parameters can also often be worked out from the velocity curves. Shown is a non-circular orbit as viewed from two different orientations. The velocity curve often reveals whether a star has more than one orbiting planet. Shown here is a velocity curve for a star with two orbiting planets. The system consists of a more massive planet, with a larger orbital period, and a less massive planet with a shorter orbital period. The red curve has been added to help you see the period of the larger planet. A measure of a planetary system's orientation is called inclination. 3 inclinations are shown. Recall that the Doppler shift only tells us radial velocity. That is, It only reveals the component of motion directly toward or away from our line of sight. If the inclination is less than 90 degrees, the Doppler data only reveals part of the star's motion, and calculations will only reveal part of the planet's orbital period, mass, speed, etc. However, if the inclination is 90 degrees, then the Doppler data reveals the entire motion of the star and will yield accurate values of the planet's orbital period, mass, speed, etc. If the inclination is 90 degrees, then the planet will occasionally pass in front of the star. This is called a transit. Transits reveal themselves by very small drops in the amount of light received from the parent star. When transits are observed, then one knows that the inclination angle is indeed 90 degrees. Any Doppler data accounts for the entire motion of the star. The amount of time it takes for the light to drop to a minimum is equal to the amount of time it takes for the planet to travel a distance equal to its diameter. If the speed of the star can be worked out, then the diameter of the planet can be calculated. Armed with both the planet's diameter and mass, its average density can be calculated. Density is helpful in determining if the planet is a Jovian or terrestrial-type planet. If the planet has an atmosphere, then starlight passing through that atmosphere during a transit will have additional or enhanced absorption lines. Thus, the composition of the atmosphere can be determined. When a planet passes behind the parent star, there will be a loss of infrared due to the blockage by the star. The infrared lost must have been the amount radiated by the planet. The measured amount of infrared light being emitted from the planet can then be used to calculate the average global temperature of the planet. Gravitational microlensing involves Einstein's view of gravity as the curvature of spacetime. The presence of mass curves the spacetime around it. Light passing by that object will follow the curvature created by the mass. When a foreground planet passes in front of a much more distant background star, the light from the background star is sort of funneled together so as to appear brighter, not dimmer. Shown is the effect of both the planet and its parent star. About a dozen exoplanets have been discovered this way.